Yeah, hi guys, welcome to the present session, and I hope my audio and video, both these two, are fine. Okay, and in this video we are going to see the electromagnetics and the transmission lines, that is as per the UGC Unit Electronic Science syllabus. So it is the 7th unit, guys. So regarding that one we are going to discuss here. And before going into the main content of this video, so myself, I am Aswini Kumar, the Unacademy educator of electronic science as well as the general paper 1. And it is my profiling, guys. So Unacademy is providing the free online classes as well as the paid courses also. And if you belongs to electronic science, or else if you are preparing for the paper 1, then my profile link is also kept in the description box of this video. So click on this follow button, and whatever the new courses or the special classes I am going to launch, okay, all those things you will get as immediate notifications. And if you want to access all my free online classes, then you just scroll down and search for the special classes, then click on the see all, and then you will be directed to the whatever the free online classes already I did. Okay, so you can access all these free online classes, you may check down. So here are so many useful electronic science as well as a PhD admission related and the general paper 1 related so many sessions are there. So the interested candidates may once have a look on this one. And if you guys are preparing for the next cycle UGC NET examination, then to get the complete course of electronic science as well as the paper 1, so the interested candidates may take the subscription plan. These are the different subscription plan, guys. So I may take any one of the subscription plan here, and you may check down. For the 6 months you get 1 month extra for free, and the offer is going to expire on December 22nd. And on 12 months you will get the 2 months extra for free, and this offer is also going to expire on December 22nd. Okay, and here the some percentage off is also there. On the 3 months 28%, and 6 months 39%, 12 months 62, and 24 months 74% off is there. So the interested candidates may take the subscription plan now itself. And apart from these savings, here I will give my referral code also, that is ASWINIKLIVE. So if you use my referral code and then click on the apply, and then you will get the 10% discount on any one of the subscription plan. Okay, you may check down, you got the 10% off. Okay, so these are the after 10%, these are the prices. Got it? So remember my referral code ASWINIKLIVE, and then proceed to pay. Okay, so whatever the plan you are going to choose, so choose that one and then proceed to pay. Got it? So it is how to take the subscription plan, guys, and this the subscription link is also there in the description box of this video. So it is my referral code ASWINIKLIVE. Got it? Fine. And now while coming to the present content of the video, as I told that the today's session is regarding the electromagnetics and transmission line. So the first one we're going to see is the main point in this one is the Maxwell's equations. So Maxwell's equations, total 4 equations are there, and these Maxwell's equations two different types we can take depending upon the mediums. So one is based upon the time static fields, and other equations are the time varying fields. Okay, so in the time static fields, what are the 4 different Maxwell's equations are there, those things we are going to see. And in the time varying fields also, what are the 4 different Maxwell's equations, that also we are going to see. And this Maxwell's equation is very important question that we are going to get a pakka 100% in our UGC NET examination. And out of the 4 different Maxwell's equations, the 2 equations we are getting from the electrostatics, and the remaining 2 equations we are getting from the magnetostatics. Got it? So whatever 2 equations you are getting in the electrostatics, so generally electrostatics is nothing but whatever the field which we got due to the static charges is called as an electrostatic field, and whatever the field we are going to get due to the moving electric charges, it is called as a magnetostatic field. Got it? So while coming to the Coulomb's law, Coulomb's law as well as the Gauss law, both these two are the important laws in the electrostatic fields. In the same way, coming to the magnetostatic fields, the Biot-Savart's law as well as the Ampere circuit's law, both these two are the important in the magnetostatic fields. Okay, so let's have a look regarding this Coulomb's law as well as the Gauss law. So if you are taking the 2 point charges, either they might be the point charges or the line charges, surface charges or the volume charges. If both the two charges are the like charges, that is positive and positive, then the repulsion force will take place. If both the two charges are the same, unlike charges, that means one is positive and another one is negative, then you will get the what we call attraction force, right? So whatever the repulsion force or else the attraction force, whatever the force is there, that can be mathematically calculated with the help of the Coulomb's law. So that is this one. So F is equal to Q Q1 Q2 by, F K Q1 Q2 by R square. So here the K is a constant, it can be given as 1 divided by 4 pi epsilon naught. Okay, and these are all the, so whatever the expression is mentioned here, this expression is regarding the what we call scalar force equation, and these expressions represents the vector force equations. Got it? Next, so coming to the electric field intensity. So electric field intensity is nothing but force per unit charge we can take, so F divided by Q. And here one problem you may check down. So the point charges 1 millicoulomb and minus 2 millicoulombs are located at these points, so calculate the force. So the interested one can look at this problem. And apart from the point charge, as I told that we are also having the line, surface and the volume charges. So usually if you take any one charge, charge density, okay, if it is a line charge density, then the rho L is equal to dq by dl, that is rate of change of charge with respect to the length. If you are taking the surface charge density, then it is dq by ds. Okay, rho S is equal to dq by ds, nothing but a surface charge density, that is rate of change of charge with respect to the surface, and in same way volume also. Okay, so if you are taking the rho L or the rho S or the rho V, so just now I told, so in these expressions, as I told that rho L, that is the line charge density, is equal to rate of change of charge with respect to the along the line, right? So from this one, the dq can be written as integration of rho L into dl, right? So that is equal to dq is equal to rho L into dl, and if I apply the integration on both the two sides, then what you will get, q is equal to rho L into dl. Okay, so that's what they mentioned here. In the same thing will happens to the what we call q is equal to rho S into ds, and the q is equal to integration of rho V into dV. Okay, next, so electric field expressions also can be written like this. And if you are taking the infinite line charge, then the amount of electric field intensity at one particular testing point. Okay, testing point is nothing but a subject point or the reference point you can take. Okay, so it is the infinite line charge that I am going to take, and it is a reference point. So at this point I want to find out the electric field intensity, and that E can be given as rho L divided by 2 pi epsilon naught into rho into E rho. Fine. And if I took this epsilon naught to the left hand side, then it becomes a D. So D is equal to epsilon naught into E is equal to rho L divided by 2 pi rho into E rho. Fine. And while coming to the infinite sheet charge, so for this one we can take the electric field intensity as like this, rho S divided by 2 epsilon naught into AN. And in the same way, here the D can be written as rho S divided by 2. Fine. And it is for the sphere expression. So coming to the electric flux density, we can take that the D is equal to epsilon naught into E, or else we can also write that D is equal to, just a minute guys. So D is equal to epsilon into E, and this epsilon can be written as epsilon naught into epsilon R into capital E. Okay, and D represents the electric flux density, that is rate of change of flux with respect to the surface, and it can be written as d phi is equal to d into ds, and if I take the integration on both the two sides, then phi is equal to integration of d into ds. That's what this expression is. Okay, and the d also can be expressed like this also. Fine. And next one is the Gauss law. So as per the Gauss law, if you take any one surface charge, okay, if here the 1 point charge, 1 point, that is the total 3 point charges are there, then whatever, positive charge means the flux will be outward, negative charge means the flux will be inward, and here also outward. Okay, so whatever the net amount of, whatever the flux is generated in this Gaussian surface, this flux can be taken as total amount of charge enclosed in the surface, that is QENC. That is what exactly the Gauss law can be expressed as. And for the flux, already we got psi is equal to here integration of d into ds. So that's what we took here. Psi is equal to integration of d into ds. And Q, we already know that the volume charge density Q is equal to integration of rho v into dv. Fine. So now if I equate both these two, I will get like this. And with the help of the Stokes theorem, the surface integral can be converted into the volume integral by taking the del dot in front of the d. Okay, then you will get the integration of del dot d dv is equal to integration rho v. So differentiation of the volume cancelled both the two sides, and finally we will get rho v is equal to del dot d. Okay. Next, for the uniform charge sphere, the electric flux density can be taken as like this. Next, coming to the work done in the displacing a charge by the dl. So that means, for example, if you take any some line charge, and if you apply the potential as like this, and if it is a negative line charge, then the negative line charge will be attracted towards the positive. If it is attracting towards the positive, means some work has to be done on this line charge, and the amount of work done can be written as dw is equal to minus f into dl, and f is can be taken as q into e, where f represents the force acting on an electron if it is kept in the electric field. Okay, so if I take the integration of both the two sides, then I will get like this w and bring this q here. So the potential can be given as a rate of change of work done per unit charge. Okay, that is work done per unit charge can be taken as a potential. Fine. And electric field as well as the potential expression also can be written like this. And the electric potential V is equal to Q divided by 4 pi epsilon naught R. Next, so if you are taking something like this, the potential from A to B and B to A. So potential from A to B means let's take VAB, and potential from B to A means let's take it is VBA. Now we can write that VAB is equal to minus VBA. And if I bring to the left hand side, then the VAB plus VBA is equal to 0. That means the total potential, that is V, becomes is equal to 0. So whenever the V becomes is equal to 0, in the previous we gone through that V is equal to minus integral E into dl. So that becomes is equal to 0. Next, so from this one we can write like this. And if I convert the line integral into the surface integral, then I need to take the del cross E here. So finally I will get the like this del cross E into ds, and if I cancel the integration of both the two sides, then the del cross E is equal to 0. So it is the Maxwell's second equation in the electrostatics, and in the same way del dot D is equal to rho v. Okay, del dot D is equal to rho v is the Maxwell's first equation in the electrostatics. Okay, so like this we will get the first equation and the second equation of the Maxwell's equations. Okay, and next one, coming to the what we call third equation. Fine. So coming to the third equation, in the previous session, as we gone through that, the flux density is equal to psi is equal to integration of d into ds, right? So this expression is for the electric field, and I can adopt this expression for the magnetic field also by substituting the d as a b. That means here the d is electric flux density, and here the b is the magnetic flux density. Got it? So now the phi is equal to integration of b into ds I can write, and what we call, if you are taking any one magnetic bar, north pole and south pole, okay, the flux lines usually the generate will like this. That means in magnetic field, the flux lines will flows from north pole to the south pole, and these flux lines are the closed loop. So due to the closed loop, at any one surface the net flux becomes is equal to 0. Okay, and if you want to break this north pole and south pole separately, but the monomagnetic pole will not exist. Why? Because if you take the magnet north and south here, if you break this bar, then north pole here, south pole here, and north pole here, south pole here, you will get like this, right? We can't able to isolate the north pole separately, south pole separately. So always the net flux becomes is equal to 0. That means the phi can be taken as 0 into integration of bds. And if I take the volume integral, means Stokes theorem, then the ds can be converted into dv by taking the del dot b into dv. So finally the del dot b is equal to 0. That will be the See, del dot B is equal to 0, so it will be the Maxwell's fourth equation. Got it? Fine. And coming to the Maxwell's third equation is that, see guys, so current density J can be written as current per unit surface area. Got it? And it can also be written as dA divided by ds, and from this one the dA can be written as J into ds, and if I apply the integration on both the two sides, then I will get I is equal to integration of J into ds. Got it? And so I can be written as integration of J into ds, okay, and I also can be written as integration of H into dl. Now if I compare both these two equations, now here I am converting the line integral into the surface integral. So whenever the line integral has to be converted to surface integral, then I need to take the del cross here. Okay. So now the here also del cross H ds and here the J ds, cancelling the surface integral on both the two sides, you will get del cross H is equal to J. Okay. So it is the Maxwell's third equation. Got it? So now we will get all the four equations. So it is all the four equations. So del dot D is equal to rho V and del cross C is equal to 0. Both these two equations we will get from the electrostatics, and del dot B is equal to 0, del cross H is equal to Z. Both these two will get from the magnetostatics. Anyhow, these are the expressions of the what we call Maxwell's equations at the static field. Four Maxwell's equations at the static field. And if you want to take the what we call, apart from the static field, if you want to take the time varying fields, okay, if you want to take the time varying fields, then out of all these four expressions, del cross E is equal to 0, del cross H is equal to Z, so both these two will be changing. Okay, so how, what the changed expression will be? So these are all the changed expressions. Okay, so del dot D is equal to rho V and del dot B, both these two are same in the static as well as the time varying, but both these two are different. So the del cross C is equal to minus dou V by dou T and del cross H is equal to J plus JD by dt. So in the del cross H expression, that is J plus JD, so this J is called as a conduction current density. Okay, this J is called as a conduction current density, and this JD is called as a convection current density. What is the difference between both these two is that conduction current density happens when the conduction happens in the metals is called as a conduction, and the convection current density means the conduction happens in the insulators. The conduction happens in the insulators is called as a convection current density, and the JD can be written as dou D by dou T, and this JD can also be called as a displacement. It can also be called as a displacement current density. Got it? Fine. So these are all the different Maxwell's equations, guys. Okay, so I hope all of you understood. Okay, so from this Maxwell's equations, definitely we will get one question in the exam. Okay, next, so coming to this one, whenever the electromagnetic waves are traveling in some medium, means here we are taking the four different types of mediums. One is a free space, second one is a lossless dielectric, third one is a lossy dielectric, fourth one is a good conductors. Okay, and we are going to differentiate the different mediums with respect to conductivity, permittivity, permeability. Okay, in the free space, sigma 0, this here epsilon r is equal to 1 and here mu r is equal to 1. In the lossless dielectric, the conductivity can be taken as 0, lossy dielectric like this, and in the good conductors we can take as like this. In the good conductors also, the relative permittivity becomes is equal to 1. Okay, and these are called as a Helmholtz wave equations. Okay, so we'll get the that is electromagnetic wave equations or the Helmholtz wave equations. With respect to electric field we'll get like this, with respect to magnetic field we'll get like this. And here the sigma represents, gamma represents the propagation constant, and alpha represents the attenuation constant, beta represents the phase constant. Okay, and alpha and beta can be expressions can be given as like this. You should remember both these two expressions. Okay, and now while coming to the relation between the H naught and E naught can be given as like this. Okay, with respect to eta, where eta represents the intrinsic impedance of the medium. Okay, so the intrinsic impedance of the medium depending upon the conductivity, permeability and the permittivity. So you can take like this, and here the u represents the phase velocity, and gamma, all of you know that gamma is nothing but a wavelength. Okay, fine. So and here this tan theta can be taken as a loss tangent. Tan theta can be taken as a loss tangent, and this tan theta can be taken as ratio of the conduction current density and the convection current density. Okay, so previously we observed that del cross H is equal to J plus JD, right? So in this one, the conduction current density J can be taken as sigma E, and the displacement current density or the convection current density can be taken as dou D by dou T, and the dou by dou T can be taken as J omega, D can be taken as epsilon naught into E or else epsilon E. If I substitute these expressions here, J omega epsilon E, then E gets cancels and you will get sigma divided by J omega epsilon. And if I take the magnitude, okay, if I took the magnitude, then I will get sigma divided by omega epsilon. That's what the expression they mentioned here. It is called as a loss tangent. Got it? And the plane waves in the lossless dielectrics can be taken as, okay, take the sigma 0 and epsilon like this, mu like this, and substitute all the expressions, so you will get like this, fine, in the lossless dielectric. And coming to the free spaces, so sigma is equal to 0 we can take, and if I substitute the sigma is equal to 0 here, then this term will be gone away. Root 1 becomes is equal to 1, so 1 minus 1 becomes is equal to 0, then alpha is equal to 0, and in this case you will get the beta is equal to like this. You will get the beta, alpha is equal to 0, beta will be get as like this. Okay, and the intrinsic impedance in the free medium can be taken as 120 pi or the 377 ohms. So it is also very most important bit, guys. Fine. And coming to the good conductors, okay, by substituting sigma as a infinity, of course we don't substitute, we will take the sigma as a much greater than omega epsilon. Okay, then we will get alpha is equal to beta, both these two will get same, phase velocity and the intrinsic impedance will get like this. And coming to the skin depth means, if you take some wire, okay, if I pass the electromagnetic wave in this one, at the starting step the electromagnetic wave strength will be 100%. If it is keep on going, it's at which point its percentage is decreasing to 37%, from 100% to 37%. This distance is called as a skin depth. Okay, and the skin depth can be taken as reciprocal of the attenuation constant. Okay, that means if the attenuation constant is more, skin depth will be less. If the attenuation constant is less, then the skin depth, that means the penetration of electromagnetic wave without losses through the cable will be more. Got it? So total these are the concepts, guys, that's what I want to tell. So if you're interested, once again just go through the recorded video to get the complete expressions. Got it? Fine, guys. So by this I'm closing this session. So tomorrow we will meet with the one more topic, guys. Okay, so thank you very much. Bye, guys. And before closing my session, so as I already told you that you just once check this what we call Coulomb's force law. So 1 millicoulomb and minus 2 millicoulombs, both these two located at both these 2 points. Okay, and you need to find out the electric force on 10 nanocoulombs. That means let's take it is 1 millicoulomb, and let's take it is minus 2 millicoulombs, and let's take it is 10 nanocoulombs. Okay, and what they are asking to find out is that you need to find out the amount of force acting on the 10 nano and I will mention the points also. 10 nanocoulombs is located at 0, 3, 1, and 1 millicoulombs is located at 3, 2, minus 1, and minus 2 millicoulombs is located at minus 1, 4. Okay, they are asking to find out how much amount of force is acting on the 10 nanocoulombs due to 1 millicoulomb as well as due to minus 2 millicoulombs. If it is a F1 and if it is a F2, then the total force acting on the 10 nanocoulombs due to both these two point charges, the total force can be taken as F1 plus F2. That's what this sigma represents. Okay, so please once check down the problem, guys. So all of you carefully check down the formula as well as the problem. And if you are having any queries in that one, then please let me know. So if you are having any queries in this problem, then put your query in the comment section, guys. Okay, no problem, no doubt. Okay, if you are having no doubt in this slide means, then I will take to the next slide to calculate the electric field E is equal to F divided by Q. So check this one also. So why I am telling, because we got one question on this topic in the previous UGC NET exam, guys. So okay guys, thank you. We'll meet in the tomorrow session. Bye guys.